Hello, so my project this year is assessing the viability of nuclear fusion as a component of energy generation. So first of all, what exactly is nuclear fusion? It is what powers our sun, and it is essentially the opposite of nuclear fission. And so what this means is instead of breaking apart a large nucleus, we are merging two smaller ones to create a larger one. So this often occurs with lower atomic numbered nucleus, such as helium or hydrogen. So as of right now, the most common one is called deuterium-tritium. And so deuterium is hydrogen 2 and tritium is hydrogen 3. And so for this to occur, the electrostatic repulsion forces need to be overcome, and the two nuclei need to come to close proximity with one another in order for the strong nuclear force to take over and the two nuclei to merge into one larger one. So for this to occur, we need very high temperatures and very high pressure in order for the fuel to be confined and dense for an extended amount of time. And what nuclear fusion reactions are trying to achieve is what's called ignition. And so this is when there are sufficient amount of nuclear fusion reactions occurring at one point for it to be self-sustaining. So I mentioned earlier that the two main fuels is deuterium and tritium. So deuterium is very abundant, so it can be easily found in seawater. There's roughly 30 grams per cubic meter. However, tritium occurs in only trace amounts in nature due to its radioactive property. And so instead we do what's called tritium breeding from lithium, where we line the reactor walls with lithium, and when a neutron escapes from the nuclear fusion reaction, it collides with a lithium nucleus, and then it produces a tritium nucleus. So there are two main types of reactors. So the first is a magnetic confinement fusion reactor, and so this makes use of magnetic fields to confine and control the plasma. And so they often have what's called a toroidal shape, so this is shaped as a donut to form a closed loop. And there are coils that go around this loop to create a magnetic field called the toroidal field, and then there's also a perpendicular component to this magnetic field, what's known as the poloidal field. So this is just another magnetic field that helps confine the plasma. And so these perpendicular magnetic fields then cause a helical path of the plasma. And there are two main types of these. So the first is a tokamak, and the second is a stellarator. So here you can see there are vertical and horizontal coils which create the toroidal and poloidal field. And then in the middle you have a central solenoid, which creates a very strong electric current within the plasma in order to confine and control the plasma better. And then this is a stellarator, and so you can see it has a more helical shape than the tokamak does. And so due to the shape, there is lower plasma currents, and so the plasma is much more stable. But obviously, however, due to its shape, it's much more difficult to design, build, and operate. And the second reactor type is an inertial confinement fusion reactor. And so this uses fusion fuel pellets and essentially shoots strong particle beams into this pellet, which would then explode. And then this causes an implosion within the fuel material, and this confines it to very high densities. And then ignition is achieved. So what are some advantages? When compared to nuclear fission, for example? The first is that there's a very limited risk of proliferation because there's no use of fissile materials such as uranium or plutonium. The second advantage is that there's no risk for meltdown because there's such precise conditions for nuclear fusion reactions to occur, so that if there were any disruptions, the plasma would immediately cool and the reaction would stop. So there's a very low chance of a runaway reaction occurring. And there's also no harmful byproducts such as CO2 or greenhouse gases. The main byproduct is helium, which is just an inert non-toxic gas. And another advantage is that the energy is very efficient because when compared to nuclear fission, it produces 4 to 5 times more energy per mass reactant. But obviously there are also some disadvantages. The first is that the entire process is still very much in its infancy, and so it could take several years before we see a successful upscale of the recent experimental successes. The second disadvantage is that it requires a lot of initial energy in order to create the very specific conditions of high temperature and high pressure, and so often the nuclear fusion reactions don't actually there isn't a net gain in energy because we're putting in more energy than we're getting out. And so nuclear fusion, as of right now, is a very active topic in research and development. However, there are still several technical obstacles that need to be overcome. It has the potential to be a clean and safe energy source. And right now, the most promising technology would be the magnetic confinement fusion reactor known as the tokamak. And so for the first few steps in creating a commercial power plant of nuclear fusion is what's known as the International Thermonuclear Experimental Reactor, known as ITER. And so what ITER hopes to achieve is to show that there can be indeed a net gain in nuclear fusion reactors, and so this would be the first steps. However, in order to address the remaining technical issues and obstacles, further funding, research, and investment would be needed. Thank you for your time.
Nice to see you again here.
Nice to see you too.
How did it go?
I think it went pretty well.
Okay, I have a small question for you because I need to talk a tiny bit about me before. When I was 12, my grandfather gave me a huge collection of magazines that were talking about physics, chemistry, and that sparked my interest, especially because they were talking at the time about fusion. And at the time, it was something like revolutionary, and they were saying, okay, in 30 years, we're going to live all in a world where energy is going to be infinite with very little nuclear waste. And then we are 28 years later, fusion is still not there. Not so many people talk about it, and then yet you are here, and then you're investigating on the topic. Can you tell me a bit more about how did you discover the subject, and what do you expect from it now?
Well, the main thing that I found inspired me was the breakthrough that happened in December in the US. And so I was reading about that, and I think that was the main thing that sparked my interest. And then over the winter break, I started to do more research, and then I thought, why not do a project on it? And then I decided to submit it to the Jonk Fuerscher.
Okay, so the breakthrough you're talking about is the one with the lasers, right? Okay, and you said during the jury that you wanted to work in that area maybe later. Is it more like the laser side that you would like to investigate, or more the ITER one?
Well, I think it's more just like nuclear in general, so this could include nuclear fission, but I haven't really decided yet.
Okay. And so how many times have you been participating now?
I think this is my fourth.
This is the fourth. It has to be a record somewhere, I think. Do you have any question?
Yes. Do you feel more confident this time, since it was your fourth time?
Yeah, I think coming back has always been very nice because everyone's been super nice and super supportive. And so I think every year it's always a very supportive environment. So I just feel more and more confident. And plus, it improves my presenting skills. So every year it gets better.
Yeah, we literally see your skills evolving on stage. You are really more and more confident. To be fair, I have been browsing through the pictures that we had on our drive to check what the people are doing, and I found the pictures of your first participation where you were literally half the size of now. Not to diminish you or anything like that, but it's really fun and nice to see that you're kind of part of the family almost now. So. Yeah, what would you say to someone who would be new to the contest and would like to participate maybe in the next years? Or
I think you should definitely do it because I don't think anyone is really a loser because everyone gets something, so you're always a winner. And everyone's super nice, so you shouldn't be scared about presenting or about the open house because it's just a very friendly environment and you get to meet other people who are doing similar science projects, and so that can also inspire you as well.
Is it a lot of work?
Yes, because you have the report and then you have the presentation and the poster to do, but I think it's worth it in the end.
So investment reward, you think the balance is pretty fair, right?
Yeah.
Okay.
Do you have in mind to participate again?
Well, I'm leaving for university next year, hopefully, so I won't be in Luxembourg anymore, but maybe if there's something life-changing happening, then I might come back.
There's just a tiny incentive, but you can still participate till you're 21, and we have plenty of people coming back from abroad to participate again. You know, just saying, just saying.
Yeah, I'll consider it.
Okay.
Perfect.
Then thanks a lot for your participation again. We wish you the best of luck for tomorrow for the award ceremony, and hope to see you soon again. In any case.
Thank you.
Thank you.
Thank you.